We are today looking or continuing considering relative orientation problems. Last week we looked into the fundamental matrix as one technique for describing the relative orientation between two images. And today I would like to look into epipolar geometry and explain you how we can exploit this technique in order to find correspondences in images or image pairs. And as a second step, I would like to introduce the essential matrix, which can be seen as a specialization of the fundamental matrix for the calibrated camera. So far we were only looking into uncalibrated cameras without any nonlinear errors. And now we want to kind of look into the question, how does this problem simplifies if we have calibrated cameras? So just as a first quick reminder about the fundamental matrix, so the most important things from last week. The fundamental matrix F is a 3x3 matrix, which is used to encode all the relative orientation information for two images or image pairs from uncalibrated cameras. What it does, it describes me how is the first image taken or the second image taken relative to the first one, but it cannot fully describe kind of the rigid body transformation between the camera poses. It can describe this only up to 5 degrees of freedom for the rigid body transformation between the camera poses. That means we miss 1 degree of freedom. And this was related to scale. So we basically, from two images that are taken, we do not know how far the camera is away from each other, and this gives us an ambiguity in scale. The fundamental matrix, however, has 7 degrees of freedom, so there are 2 more, and these 2 degrees of freedom are related to the intrinsics, so affect the calibration of the cameras. So what we have from our 7 degrees of freedom, we have 5 for the relative pose and 2 for the intrinsics. And it's kind of important to distinguish between pose and orientation here. So if we talk about the extrinsics or exterior orientation, we typically talk about this rigid body transformation with 6 degrees of freedom. So relative orientation here describes, in this case, has only 5 degrees of freedom for the pose and 2 for the intrinsics, which is less than what we have in general, which would be 11 for the absolute orientation of one camera. And we are kind of looking into the special case today for the essential matrix. And then we will only have 5 degrees of freedom because we assume to have a calibrated camera. What we've also seen last week is that we can compute the fundamental matrix very easily, given that we have the two projection matrices, so P prime and P double prime, so for the first image and for the second image. So if we have those two matrices, we can compute the fundamental matrix directly. In general, the fundamental matrix has this form. So it depends on a couple of matrices. The first one here is the calibration matrix of the first camera. The rotation matrix of the first camera, so how is this camera oriented in space. Then we have this screw symmetric matrix B, which has 3 degrees of freedom and which is a singular matrix, and it encodes, so it has this vector B here, which is the baseline. So what's the direction of the second camera with respect to the first camera. And in here we have this ambiguity in terms of the scale. So we don't know, we know on which direction vector the camera sits with respect to the first one, but we do not know at which distance they are oriented with respect to each other. Then we have the second rotation matrix the rotation matrix for the second camera and the calibration matrix for the second camera. So these are the ingredients for the fundamental matrix. And one of the key things how we can exploit that is for formulating so-called coplanarity constraint, which says if we have an image, a point in our first image, and the second 3D point generated this point x double prime in the second image, then this constraint must hold. So that x prime transposed fundamental matrix x double prime is equal to 0. So there's one constraint that must hold for corresponding points. And then we also showed how we can actually exploit that in order to formulate a correspondence test. So given 2 points, we can do a test if they are likely to be corresponding points, depending how far this value is actually away from 0. And then this statistical test was dependent on how accurately can I measure my points in my images and how accurately do I know the individual elements of the fundamental matrix. The important thing is this is a coplanarity constraint formulated for uncalibrated cameras. This is how the fundamental matrix is defined. We need to know that we can compute it easily if we know the projection matrices, has 7 degrees of freedom, and it encodes the relative orientation information. It's kind of the most important ingredients. This is kind of what you need to know and need to keep in mind for the remaining part of this course, at least up to Christmas. This will be an essential part in a lot of elements. So what we're going to do today, we have a look into the so-called epipolar geometry, which we started to look a little bit into last week in order to formulate the coplanarity constraint. Then we will exploit that to derive the essential matrix, which is the special form of the fundamental matrix for calibrated cameras. And then the question is, given we have those parameters derived this essential matrix, how can we actually parameterize it? And there are kind of 3 typical ways on how this can be done. We will look into these 3 popular parameterization for describing the relative orientation. And finally, we'll look into the case how I can actually generate normalized stereo images, given that the cameras which have taken those images were not, at least not perfectly, in the normal stereo case. So it's kind of the outline for today. We'll start with the first one, the basics of epipolar geometry. So the first thing is, why should that be interesting? So we all should ask the why question. So what we want to do is, given we have a point in the first image, we want to find the corresponding point in the second image. So this is a very common problem. Often we assume those corresponding points to be given, but in practice we actually have to search for those corresponding points. So how can I do that? I can pick one point in my first image and then can say, okay, where in my second image is a point which looks very similar to this first image, just from its appearance in the intensity values, maybe also taking into account its neighbors. There may be more advanced kind of features or local patterns I may extract, but that's basically the very, very naive approach to do that. I pick a point in the first image and I say, where's a region that looks similar to this region around the point I picked in the other image? Then I say these 2 guys are corresponding points. So if I want to search for this corresponding point in the second image, I have a 2D search problem, because I need to search through my whole image, through the X and Y space in my image. So I basically need to search the whole image in order to come up with those corresponding points. This is bad for 2 reasons. The first thing is it is time consuming. It would be nicer to kind of restrict our search space. So can I kind of reduce this search space from searching the whole image, maybe in searching only a small fraction of the image. And the second thing is, if I can constrain my search space, that I know a large fraction of the image is actually irrelevant for finding these corresponding points, this also reduces possible errors, because I may have parts in my image which look very similar, just kind of self-similar objects. And then I can exclude a couple of objects which may look the same and for which I'm looking for this corresponding point, and I can narrow down the possible hypotheses for corresponding points if I reduce my search space. So the goal is, how can I avoid searching through the whole image if I'm looking for corresponding points? And this is important for 2 reasons. First, in terms of speed, I need to consider less points, and in terms of potential errors or data association errors or errors in corresponding points that I can do. If I have less elements to look into, there's a smaller probability of making an error. Okay? And what we see today is that we can reduce the search space from the 2D search space, which consists of the whole image. We can actually reduce this to a 1D search space. And this is actually a line. So there will be a line going through our image, and we know for a point in image number 1, if we want to find the corresponding point in image number 2, we only have to search along a line, which dramatically simplifies the problem that we have. We have seen something similar already for the stereo normal case in Photogrammetry 1, when we're looking for these correspondences, or for this chapter called matching. And now we can actually do that for the general case. Okay, so this is one of the very, very central figures that will actually pop up a few times, and there are several important elements in here. So let's go through those elements. What do we see in here? So this is the first image over here. This is my image plane. and correspondingly, or accordingly, this is the image number 2. The projection center of the second camera and the projection center of the first camera. And x and y are simply 2 points in space, in my 3D space. So I'm looking now into this point x. So this point is projected through the projection center into this point here. So the projection of the point x into my image. And the same happens for the image number 2. Okay, and there are several important elements which we need to consider here. So the first element is this b over here. So this b is something which is called the epipolar axis, and this is basically the line pathing through the 2 projection centers. So I'm connecting those 2 projection centers, and this line over here, so this dashed line over here, is the so-called epipolar axis. We'll soon see why it is called an axis. So the next thing we need to look into, and that's something we exploited already last week, is actually looking into the plane which is spanned by the projection centers and the point that I'm considering. So this point x, O prime and O double prime. And this is a so-called epipolar plane epsilon, and this epipolar plane epsilon depends, of course, on the point that I'm considering in space. And we exploited that this is a plane last week in order to formulate the coplanarity constraint, which guided us to the formulation of the fundamental matrix. So this thing over here is a plane in the 3D world, defined by 3 points, which are the 2 projection centers of my camera and the point that I'm considering. Okay, then there's another important thing, which are the epipoles. There are 2 epipoles, E prime and E double prime over here, and the epipole is the projection of the projection center of the other camera into the camera I'm considering. So this epipole is the projection of the camera center into my image. So I'm projecting this point over here into my image, and this gives me the epipole. So the epipole in the first image is the projection center of the second camera projected into the first camera. And of course the other way around. If I need to generate this epipole over here, I take the projection center of the first camera and project it into the second image. This is also a very important point that we can find. And the next important quantity is this line over here, which connects this epipole and the point x projected into my image. And this is the so-called epipolar line. And these epipolar lines are kind of important elements for this search that we will see. So these are kind of the 4 elementary quantities or entities of the epipolar geometry. And what we are going to do now is actually how are those guys defined, and then exploit this definition to derive properties in this epipolar geometry. That's kind of the plan for the first hour here. So is there any question about this image at the moment? Yes, please.
Was passiert, wenn die Ebenen links und rechts sich so weiter quasi mehr, die stehen ja jetzt so zueinander,
Ja.
wenn die so zueinander stehen, dass jetzt quasi die Epipole gar nicht mehr in dem Bild liegen, so sehr weit gleich weiter.
Okay, so the question is, those camera setup goes towards the stereonormal case, those epipoles may not be mapped into the image plane. That can definitely happen. Then this epipole simply lies outside the image plane. So if you would make this, so it can in theory lie outside or even towards infinity. That's possible. So in the projective space, we can express points at infinity, so this point would move towards infinity as the more I approach the stereonormal case. Any further questions? Okay. So then, let's continue and start with the epipolar axis. How is the epipolar axis defined? That's done quite easily. There's just the line going through the points to the two projection centers O prime and O double prime. So I'm just the line passing through those 2 points defines my epipolar axis. And also the epipolar plane is very easily defined. It's just the plane that is spanned by the 2 projection centers and the point that I'm considering the 3D space. And then what I'm going to do now, or what we're going to do in the following, we actually exploit this epipolar plane in order to look for correspondences. Okay, the first thing that we can actually have a look into, we have our epipolar plane, we have our point x, and if this point x moves in space, say moves up and down here, this basically means that I'm rotating this plane. The plane is fixed by those 2 projection centers, so the projection centers do not change within one image, but I get multiples of those epipolar planes, and they depend on the point in the 3D space that I'm considering. So I've kind of, okay, something to illustrate that. Okay, let's take this guy over here. So this is the projection center of my of the second camera and the projection center of the first camera, and I take the point somewhere in space. This kind of illustrates the plane. If I move it up and down, I get multiple epipolar planes, but they all include this axis. So you can see it's a rotation axis of the possible epipolar planes. That's also the reason why it's called axis. Okay? So, but that also means that we don't have, so the space of epipolar planes is actually constrained. So they're not all possible planes in space possible. Only those which path include those 2 points over here. Okay, and then we have the epipoles. We said the epipoles, the first epipole, the one in the left image, is actually the projection center of the second image projected into the first image. So it was this notation means here. In brackets, and a prime or double prime means projected in the first image or projected in the second image. And the second epipole is the projection center of the first camera projected into the second image. And then I can actually also define these epipolar lines. And the epipolar line is defined by projecting the line from the projection center and the corresponding point into the other image. So for the epipolar line in the first image, it's the projection center of the second camera's projection center and the corresponding point. And the same for the other one. So we can see that if we look to this epipolar line, what does that mean, this epipolar line? It basically means that every point which lies on this line, on this ray, which passes through the projection center of the other camera towards the point I'm considering and can continue even further. That every point on this line is actually projected onto this line over here. So this line even extends over here. So that means if I'm picking a point in my second image, I know where it's mapped to, so at this point over here, then I know the point in the 3D world somewhere lies along this line. And if I can take this line and project it into the other image, I know that the corresponding point in the second image must lie along this line. And this is how we actually reduce the search space from a 2D space where we would need to search the whole image into a 1D space. But you can also see if you have all these epipolar lines over here, that actually all epipolar lines actually pass through an epipole. Because the epipole is a projection of the projection center of the other camera into this image over here, over there. So whatever point x we take, if it's x, y, or a different point, the ray always passes through the projection center, and therefore the epipole is an element of all epipolar lines. So if I look for correspondences, what I basically need to do is I need to construct my epipolar line and then search along this epipolar line from the epipole in order to find the corresponding point. Is this geometric relation clear? So Just to briefly summarize it again. If I have a point over somewhere in space, and I only observe this point with this camera image, I do not know where this point is in terms of the distance from the camera. I only know that it lies on this line. And if I take this line and project this line into the other image, I actually generate this search space along which I have to look for finding the pixel that corresponds to the mapping of this point X. It's somewhere along this line over here. And the advantage is that this reduces the search space. If I search for a corresponding point, I only need to search along a line. I don't need to search the whole image, which is first faster, and second, there's a smaller probability that I actually make an error because I have, let's say, multiple points which look similar in space.
So if I understood you correctly, I think you made that example of the point U already. So if the point U moves around the line X to O prime, then
yes,
it will always move on the right image on the line P, what do you say, double,
yep,
double prime to E double prime.
Yeah, so that's true. So it doesn't matter if I do it from this image into this image or the other way around. So if I have this point, but it's absolutely right what you say. If I move this point U along this line, it will be projected along this line. This is exactly the search space I'm considering.
So I get the distance information of the point U to O prime by finding that projected point on the line P double prime to E double prime.
So if I know where this point is mapped to, then I can reconstruct the depth information. And this is the principle of stereo vision, that also what we have with our human eyes, that we have two cameras which sit spatially apart from each other. They observe a scene, and by our brain doing the correspondences, we can actually estimate the depth of an object, how far it is away. It's the same here. Based on how far those points are away, so based on this distance over here, so where this point is mapped here, so what's kind of the offset along this line, we are actually able to infer depth information.
So we don't do it by measuring kind of an angle, which would be another possibility, but by measuring the distance between P double prime, U double prime, and P double prime, etc.
So they of course correspond to each other in the end. So every pixel corresponds to a certain angular measurement. But so note that the problem here is slightly different from what we had before. Before we said we have a point in space where we know where this point is and we map it actually to the individual images. What we now want to do is we actually want to search for correspondences. So we don't know which point in the first image corresponds to a point in the second image. We want to look for those correspondences. We want to search those correspondences. So I just pick one in the first image and then search for a similar looking area in the second image along these lines. Once I've found it, and assuming it's correct, I can infer how far the point is away and then obtain an estimate of it about its 3D location in space. Okay, any further questions about these concepts here so far? Okay. So this is something that we have already. So we now can have a look and can look a bit more into these epipoles and epipolar lines. So we said the epipoles are the projections of the projection centers into the other images, but we can also write them as the intersection of the line which connects the first projection center and the second projection center and the image plane of the first camera. We can do the second thing. For the second epipole is a line connecting the two projection centers intersected with the image plane. So it's an intersection of a line and a plane. And this also gives me the epipole. So just from a geometric point of view, this is just the intersection of this plane and this line, or this line and this plane, which gives me the two epipoles. And we can do something very similar with the epipolar lines. We can say the epipolar lines can also be written as the intersection of the image plane of the first image and our epipolar plane. So now we are intersecting two planes, which gives us a line. We can do this for the first image and the second image. So I'm taking this epipolar plane, which is influenced by this point. So depending the point I'm considering, this gives me an epipolar line, and the image plane, of course, stays the same. But it's kind of from a geometric point of view, the intersection of both. You can actually see that here. Well, this actually doesn't add something very new. So this is the epipolar plane, epsilon, and intersecting this plane with this image plane gives me exactly this line. And here again, I obtain this line over here. So the important thing is that all those quantities that we are considering, basically the two projection centers, the point in my 3D world, the epipoles, and the image points all lie within the epipolar plane. And the epipolar plane is only defined by the projection centers of the cameras and the point in the 3D world that I'm considering. Defined by nothing else. And all the searches that I can do for finding elements, so actually I can restrict my search through this plane, or even reduce it further, restricting the search by intersecting the plane and, for example, the image plane if I look for an element in the image, which is typically the case. So this fact that all those elements lie within the epipolar plane allows me to simplify the task of looking for corresponding points in the other image. So given I select a pixel in my first image, which pixels do I need to inspect in the second image in order to find the corresponding point? And this fact is a fact that helps me to reduce this search space. So again, this is basically a somewhat verbose repetition of what I told before. The task is predict the location x2, so the point in the second image, given I know where the point is in the first image. I know the epipolar plane. I can construct the epipolar plane. The important thing over here is that this epipolar plane does not depend on the point that I'm searching, only on the input point for which I'm searching the corresponding point. So if this would depend on x double prime, that wouldn't help me. But as it only depends on x prime, that's why the arrow is here, I can construct this epipolar plane and then use this epipolar plane by intersecting it with the other image in order to find the projection of this point by intersecting the epipolar plane and the image plane, which in this intersection is the epipolar line. So what I need to do is I just have to search along these epipolar lines. And again, this important thing is that I just have to search along a line that reduces my search space from a 2D space to a 1D space. So these are kind of the very, very essential elements why this so-called epipolar geometry is useful and simplifies the problems when we talk about corresponding points, finding corresponding points. Again, you can even use this for testing, very similar to how we have done that last week by saying, actually, how far are we actually away from this epipolar plane? Of course, there's not a one-to-one correspondences because there are multiple points which can lie in the epipolar plane and can be possible corresponding points. But if I know that a point is not in the epipolar plane, I can make the statement that it is not a corresponding point, at least if it is far away from this plane. Okay? So there's very basic ideas of epipolar geometry clear. We have these four important entities, and with those entities, I can construct these epipolar lines, which are the reduced search space when I look for corresponding points. Okay, so the next thing is how do I actually compute that in practice? How can I compute the key elements or key entities of the epipolar geometry in order to come up, to describe those elements so that I can use this in practice to construct these epipolar lines and look for correspondences. What we're going to do is in here is that the only thing we actually need are the projection matrices over here and the fundamental matrix, but the fundamental matrix we can actually obtain from the projection matrices. We want to kind of derive these geometric elements in here. Okay, so the first thing is what we need to describe is the Epipolar Axis, so our B, which is a line connecting our two projection centers. We can actually do that by just subtracting them. This gives me the direction vector, in this case, from the first camera image to the second camera. From the projection center of the first camera to the projection center of the second camera. And we only know its direction. We do not know where it is along this line. So we express this by a homogeneous vector, just subtracting those points, so we just encode the direction. So note that this only encodes the direction, and this is not a line constructed in homogeneous coordinates, because I wouldn't, just subtracting 2 points in the homogeneous space doesn't provide me with a line. So what we are looking here, we see this as a direction vector. I have 2 points, I subtract these points, and I get the direction vector over here. And homogeneous, as we don't know, basically know its scale. So the next thing that we actually want to look into is how do we actually obtain these epipolar lines. So we know that the point in the point in the first image must lie on this epipolar line that I'm looking into. And if we look back to the lecture on projective geometry in the end of the Photogrammetry I course, we know that we can use the scalar product or dot product of a point and a line in homogeneous coordinates. And if this product is 0, then we know that this point lies on that line. Okay? So is everyone aware of this fact? So if we have a point in the line, we want to test if this point lies on that line. We just need to compute the dot product. If it's 0, they lie on that line. Otherwise, they don't. So I can express this fact saying x prime transposed times the epipolar line, which I want to compute, must be 0. Okay? So I can now look to this expression over here. And there's an expression that we used a lot last week. We say this x prime transpose times something should be 0 for those corresponding points. And this was exactly what the fundamental matrix was doing. So the fundamental matrix was saying x prime transposed f x double prime should be 0. If I take those two equations into account, so this part is the same, this part is the same, this part is the same, you can say, okay, and if I look to those two equations which must hold, because this is a corresponding point, then L prime actually equals to f times x double prime. So just by combining these facts, I can infer that this must be L prime. So the first epipolar line is given by just the fundamental matrix times the point in the second image. So I can just take the point in the second image, multiply the fundamental matrix with this point, and I actually obtain the line in homogeneous coordinates in the first image. So it's very easy to do. So given the point x double prime, just f times x double prime gives me my epipolar line. And this also kind of maybe underlines the fact that the matrix F encodes all the information that we have about the relative orientation of those two images. Because nothing else is needed in order to tell me where the point, on which line a point from the second image is mapped to in the first image. So this encodes all the relative orientation information that we have about those two images. Okay, once we did it in one direction, we can, of course, do the same thing in the other direction. We can say, okay, also the second epipolar line multiplied with the second point must be 0. It can exploit exactly the same fact. And as a result, L transposed must be equal to x prime transposed times f. So as a result of that, L double prime is simply this expression transposed. So I need to compute the transposed fundamental matrix and multiply it by the coordinates of the point in the first image, and this gives me the epipolar line in the second image. And this is exactly the prediction about where the point lies, so this reduced 1D search space that I can compute when I have my point in the first image and want to estimate where it is in the second image. So this is from first to second image. I have to do it like this. And if I'm going from the second image to the first image, this is the key equation that I need to exploit. Okay, so in sum, what we have, basically a summary of what we did before. What we exploited is we exploited the fact that the points we are looking into must lie on this epipolar line. We formulated the constraint based on that. We have seen that we have the coplanarity constraint from the fundamental matrix, which allows me to define a very similar constraint. And just by exploiting those two equations, I have those two relations over here which tell me how one point, on which line a point is mapped in the other image. Kind of this is the very essential part for that. So this is how I construct the search space. So the only thing I need is actually the fundamental matrix. I need to know where the points are, and then I can construct these epipolar lines in the images. Any questions about that up to this point? Okay, so the next thing is then how we can actually compute our epipoles. We said our epipoles were the projection of the other camera's projection center into the image of the camera. So that's very, very easy to do. As we have assumed to have the projection matrix, and if we have the projection center of the other camera, we can simply write this as the second projection center projected with the projection matrix of the first camera gives me the epipole in the image 1, and here the other way around. So I'm taking the first camera's projection center, mapping it with the second camera, I've obtained the second epipole. So these are these epipoles over here, and the important message, I said that before, that all epipolar lines path through the epipoles. So all the different epipolar lines that I have all path through these points. So we have this fact that for all lines, epipolar lines in the first image, the epipole dot product, the epipolar line must be 0. So this is expresses the fact that the epipole, which is a point, lies on this line homogeneous coordinates. And the second thing holds, of course, for the second image. Oops. So if I put this together, I say, okay, for every L, E transpose times L must be 0. This holds for both images. If I now put the definition of what an epipolar line is into L by saying L prime is F times X double prime, I actually obtain this expression over here. So the epipole transpose times F and any X, so any point X is 0. So that means that this epipole actually is the null space of the fundamental matrix. So we can express this that the epipoles are the null space of the fundamental matrix. So all vectors are multiplied. So if I E, F, and another vector multiplied will always give me 0. And this is the point, or they correspond to the eigenvalues of 0. So the eigenvectors which corresponds to the eigenvalues of 0. Okay, so to summarize the epipolar geometry so far. So the only thing we assumed so far were uncalibrated cameras. So we have not yet entered the essential matrix for calibrated cameras. We stayed in our uncalibrated world, assuming only that we have no nonlinear errors. So everything can be expressed. So the calibration matrix has up to 5 degrees of freedom. We discussed the epipolar geometry and its 4 essential quantities, so the epipolar axis, epipolar plane, epipoles, and epipolar lines. We derived how we can actually compute them only knowing the projection matrices and the fundamental matrix. And the key insight, or why this is so important, is that the epipolar geometry allows me to reduce my search space if I'm looking for correspondences. Kind of the key take-home message for this chapter on epipolar geometry. So are there any questions about this epipolar geometry up to now? Yes, please.
It only works for points within this triangle. What about points outside of the triangle? You had it in your picture, the Y point, for example.
So the Y point, so this triangle is kind of the epipolar plane. Oh, sorry. The question was, what happens for points which lie outside this triangle over here? So this triangle, what is indicated here as this triangle is actually the epipolar plane, which corresponds to this point X over here. If we look to the point Y over here, we would simply construct a different epipolar plane. And this is the epipolar plane, which is defined like this over here. And then we get it's a different point which defines this epipolar plane. So we will have a different plane, but we still know that this axis passes through that plane. So we will get a different epipolar line. So this is the corresponding epipolar line for the point Y. So every point generates an own epipolar line. Of course, it can happen that this epipolar line is outside the image. That simply means it's the photons corresponding to this point didn't touch my sensor. I simply have no information where they are, except that I know that they must lie somewhere on a line. Did this answer your question? Okay. Any further questions? Yes, please.
Man kann ja mit der Kamera quasi nur nach vorne gucken. Das heißt, man guckt doch eigentlich von dem Bild in das Projektionszentrum, wenn man jetzt anderswo ist.
Yeah. Okay, so this is, I can actually rotate that to the other side, but the all quantities still hold.
Können diese epipolaren Flächen, kann man die komplett in die Rotationsachse drehen? Eigentlich kann man doch nur einen bestimmten Winkel sehen an sich.
Okay, so the question was if we can rotate the epipolar planes fully around this axis over here, because we only have a limited field of view in our images. Was this the correct question? Of course, this is the case. So it may be the case. So they will all, as long as the epipole is part of the image, a part of this epipolar line will always be visible in an image, but there will always be a part of the epipolar line which will not be visible. And even if we they will not always, but there can definitely be parts of the epipolar plane which is not visible, because what I'm basically doing, I'm intersecting a plane with another plane, and the second plane is actually limited in its extent. So there can definitely be intersections which are outside the plane. So it simply means that it can happen, for example, if I select one point in image number 1, but this point has not been mapped by the second camera image because it's outside the field of view. I will generate an epipolar plane, and I know if the chip on the other camera might be larger, it would have been mapped, but if it's outside the visible area, I have no chance to find a corresponding points, because the corresponding points has not been mapped by the other camera. So I still, if I'm doing my search and I construct these lines, I still, of course, need to check that I'm in the visible area of that camera. So the cameras have a field of view, but this field of view have not been considered here in this geometry. Did this answer the question? Or not really? If not, please try again.
Ja, da hätte ich aber noch das andere. Man hat was ich mir dachte, diese epipolaren Linien, die ja dann quasi nur, die fahren nur einen bestimmten Winkel ab quasi unten. Das ist quasi auf der anderen Seite von dem.
So these epipolar lines can be extended here. The point goes further towards infinity. So this line will extend over here until the point reaches infinity. And it, of course, here as well, but here I'm typically already, but this can happen. If I have a very wide angle field of view, they do here as well. So if I have a point which lies, so you mean it lies behind this camera, so this camera would obstruct the field of view of the other camera? Yeah. So over here. Yeah. So, okay. No. So this triangle, So the plane is just visualized by 3 points. This is not necessarily a triangle. This is a full plane. And of course, the plane also extends in this area here. So it depends. I can have a camera which has a field of view which is larger than 180 degrees with a corresponding lens. I can actually generate that. At some point in time, the math, you may get singularities in here because the math cannot, if you have very large field of view cameras. But in theory, this is a full plane. So I'm just looking here, these kind of bundles of rays, or Strahlenbündel in German, which I'm looking into here. And I'm not taking into account any visibility constraints. I'm just looking into these bundles of rays which all pass through the projection centers. This is kind of the geometry that I want to describe, that I described with this epipolar geometry. So field of view information is not considered here. Okay? Any further questions at that point? Okay, if this is not the case, we'll make a 5-minute break, and then we're going to continue.